Excellent. Thank you so much. So hi, yeah, my name is Ilana Wisby. I'm the CEO of Oxford Quantum Circuits. And what I'm going to do today is first just kind of give you an introduction into who we are and some of our core technology, some results from that as well, before kind of a broader scope of the ecosystem. Generically, who we are? Well, we are a company. We build quantum computers. We build the actual hardware itself. We're a spin out from the University of Oxford. And it's really our mission to build systems that can help enable, quantum to be delivered to the brightest and smartest minds so that they can do super interesting things on them and solve some of the world's most pressing problems. And we do that, of course, by delivering the technology itself, and we deliver that through a quantum compute as a service mechanism. And the reason that I want to highlight this is as a team, this is our mission. This is absolutely why every single person in our company is driven to work for OQC, is to make a difference. It's of course also because they have an incredible job where they get to do incredibly interesting things with an incredible team of individuals. And I'm going to run through a few of the key players in the team today. So of course myself, I am the founding CEO. My background is I have a PhD in hybrid quantum systems. That was superconducting systems coupled to silicon spins, and also a two-level systems slow noise processing background as well from my time at the National Physical Laboratories. But I am very much more a deep tech entrepreneur. I left academia after my PhD and did a number of different startups before coming in as the founding CEO of OQC. Now, next key player we have is Dr. Peter Leek. Now, Peter Leek is probably a name that you all recognize. He is a pioneer, a visionary, an inventor, and the founder of Oxford Quantum Circuits. He works in the university with his university group, the Leek Labs, and he also works closely with the company as well. And I'll go into wider parts of the team a bit later on, but just as a quick brief, we're around 26 people today. We've got a really mixed background of academic, commercial, and industrial experience, and we're currently growing week by week. All right, so let's talk about what we do. What we do and what we don't do. So we do anything at the back end, starting from a lightweight QCAS platform, all the way through. We have in-house quantum control software, control hardware, as well as our own quantum processors, so our QPUs itself. And that'll be the main focus of the session today. But I do want to highlight that, of course, you can build qubits, but you don't have a quantum computer just with a few qubits. It's much more of a systems approach that you need to take in order to be able to deliver value. And to be able to deliver value, you need to be able to deliver something that is useful. Now, we all know that to start delivering something that's useful, a minimal viable product as such, there are three key things that we need to be able to achieve in terms of overall systems performance, and that absolutely then translates down to the qubit device level also. So the first of that is scale. We all know scalability is a key issue. We need to have many more qubits, 50 to maybe 250 or a few hundred for the NISQ era, then starting to go into the tens of thousands or more for our fault tolerant regime. Our qubits need to have high quality, so low error rates and high coherence times, and the functionality needs to be in place as well. Of course, that's qubit functionality, i.e. how we're getting them talking to each other in terms of coupling mechanisms on and off, but also then starting to think about the depth, the connectivity, and even more broadly on the systems level, of course, then low latency control hardware, all of the different layers. And ultimately as a system, once we have scale, quality, and functionality in tandem, we'll be able to have high performance, useful quantum computers. So what I'm going to touch on is OQC's unique approach to building quantum computers, and really where we span out from the University of Oxford from, which is our core IP. Our core IP is a qubit. It's called the coaxmon, and you'll understand more why in a moment. It is liberated from the constraints of 2D technology, and it is simple, it is scalable, and it's flexible. And right there you can see a wafer of coaxmons that usually sit in my handbag, but are today on the screen there. Now, before I talk about the coaxmon, I want to just cover some of the key components and key things that we need to consider in terms of building traditional superconducting circuits, so that we can then start to consider and address their scaling challenges that are associated with them. So a traditional example of a qubit architecture is here. This is a picture of a 2xmon style qubit. It's a UCSB Google device here. They always have the best pictures for presentations. So what you can see at the top here is a microwave transmission line. You can then see that you've got this quarter wave resonator. Here it's like a quarter wave coplanar. And that resonator could be many different types. It could also be a 3D cavity. It could be lumped element with a meandering inductor and capacitor, or it could be coaxial in shape, much like OQCs coaxmon is. Now, if you head down below the quarter wave resonator, you then hit your qubits. Now here we've got these examples, the qubits are the crosses, and here that's an xmon qubit. We also know that there are many different types of qubits and ways that we can start to build qubits using superconducting systems. Now, right at the bottom of that, you can then see this thin microwave transmission line, and that's a qubit signal line. So that's the signal line that's able to then send the signal to each qubit, and then the resonator can start to read it out and take the mechanism back. Now, if we start to think of those components are needed in order to be able to do any type of quantum computation and to manipulate any type of superconducting qubit in CQED. So things that we need to consider: resonators and what they should and shouldn't do. So we want the resonators coupling to the qubit that it's attached to. So, oh yeah, you can see my screen. This qubit, for example, this resonator would need to connect to this qubit. This resonator would need to be connecting to this qubit. What you don't want is things to get mismatched and crossed and things to start talking to each other and connecting to each other in ways that you don't necessarily want. So if an adjacent resonator to a diagonal qubit were to be connecting and talking, then you're going to get errors, and that's bad. You've also got your coupler here. Of course, coupling is two-way, so that's how the qubit and the resonator connect. Again, you want to make sure that it's just the coupler working here and the xmon here. Now, you can start to have qubits coupling in different ways. Here we've got nearest neighbor qubit coupling, but there are other different ways in which you can start to couple the qubits as well. You can start to see different techniques where you've got transmission lines between the qubits acting as a bus, or you can start to have another qubit that you put in between, and that can become a tunable coupler. So you can have that qubit that tunes itself in and out so that you can turn on and off the interactions between the qubits by bringing them in and out of resonance. So lots of flexibility, and there's tons of additional novel different types of qubit coupling mechanisms, as well as qubit device designs that still are coming out from academia every month. So it's still a really rapidly evolving space. But this is basically the core and the components that we need. So let's ask ourselves, if we take that core and we break it down and we call it a unit cell, how does that start to scale? So here on the left now, we've broken that down into a unit cell. And what we do is we start to repeat that unit cell pattern continuously, adding more and more of these. Now, this photo on the right is one of, again, UCSB's chips. It's from around 5 years ago now, with the Martinez group. Again, just has the nicest photos. You can really start to see clearly that you've got that unit cell, which is repeated again and again and again to create larger quantum systems. By doing it in this way, though, you can start to see immediately that it's presenting some challenges. For a start, how much of that chip is qubits and how much of that chip is wiring? And we can already start to see that that wiring is, getting pretty tight, particularly around the edges of the qubits. And you have to make sure that the wires kind of transverse. They can't go across each other yet if you do it in this way. So again, and of course, the more wires you add, the more loss there is, the more opportunities there are for crosstalk, for coupling to two-level systems, for examples, and that's just not good. So there's a few things here that ultimately means that the larger you go, everything is signaling to the fact that you're going to need to have some sort of fundamental design change in order to scale with that scale, quality, and control functionality effectively. So let's think about how we might do that, what typically happens when we start to think about scaling superconducting circuits in more traditional ways. Now, before I do that, what I want to do is just to take a step back and talk about qubit performance. So that we can start to measure the impact. Now, this is of course something that you're probably all very familiar with. On the left here, we have that block sphere. And what we're talking about here are T1 times. So that would be if you're sending a pi pulse from your 0 to your 1, how long it's going to take to relax back to your 0 state, which is effectively saying, how long is it taking for my energy to decay? And ultimately, that is the relaxation time of the T1. And what we can do is we can measure this. So we can see that green pulse, that would be a flip with a pi pulse, taking you from your 0 to your 1. You wait some period of time, and then you do a readout measurement, and you say, okay, is my qubit in a 0 or a 1 state? And of course, this is a probabilistic measurement. So we need to do this quite a number of times. And overall, we then get this plot on the right, which shows us that at very short time periods, pretty much it's always still in the 1 state, and in very long time periods, we can see that it's in the 0 state. And that decay is effectively an exponential decay, and that will give us a time constant of T1, which is our energy relaxation rate. And that really is the question of how long does energy remain within the qubit before it dissipates, in plain English, which is fundamental and a fundamental limitation to what you can start to do with any type of qubit. Now, like any typical ring down time, which effectively this is a process, this is a ring down process, it's going to have a quality factor associated with it. If you plug in the frequency of your qubit into that equation at the top, then you ultimately get a quality factor which defines, again, the performance and the quality of that qubit. Moving on, this is probably a plot that you've seen many times before as well, and there are many different versions of this plot. Ultimately, what this shows is that coherence time, that T1 time, and the progress across many different qubit types per year. And what we can effectively say pretty quickly is, look, year on year, there is progress and the coherence times are getting better and better and better. Now, ultimately, we can have a benchmark. We can say what defines a good enough qubit. Typically, this is probably around the 100 microsecond mark that we start being really satisfied with having high quality qubits, which translates to around a 3.5 million quality factor, a Q. Now, this is really cool because this is very similar to the type of quality factors and the type of coherence times you get from natural atoms. So if you just take a step back and think about that statement for a moment, what we're saying here is that engineers can make systems, quantum systems, that perform as well as the systems that nature provides. That's just incredible. And that's, I mean, it blows my mind. It's really cool. Back to the data. Now, I've cheated a little bit because here we're talking about single qubits still. They're single, they're uncoupled, they're planar. So we're still talking about those unit cells that I was talking about earlier. None of these coherence times in that progress reflects being able to build superconducting quantum processors, QPUs that can do useful things, which have scale and functionality and control. And T1 is always going to be that fundamental limiting factor. So what approaches are typically then taken, and how does that impact our T1 times? So immediately we decide that 1D is not good enough. We need to go 2D. And we tend to do that in a number of different mechanisms. And I say we here, talking about the royal we as in the field in general. And this is with either typically air bridges. This means that you can start to have wires that go over other wires, which means that that helps with that picture that you saw earlier and the network of wiring that you might need taken to your outer perimeter, allowing lines to cross each other. You also have vias, which are typically used through silicon vias inspired from the semiconductor industry that connect the top and the bottom of your chip through the chip. You've also got here flip chips, which is effectively moving all of your qubits onto one chip, your control mechanism on the other, and then creating a qubit sandwich connecting them with typically indium, so that you've got a superconductor between them and a low loss signal connection there. Now, if we start to think about those different mechanisms, and they are all incredibly smart engineering, then what we do still need to consider is the impact on that of our T1, and are these processes truly scalable? Let's just touch on the flip chipping here. So this is some data from MIT. It's from the same paper as the schematic previously. And what they find is that, I mean, typically they can create T1s of 100 microsecond without any bother. Once they flip chip, there is 10 times worse performance from their demonstrations. So this multi-chip model really does add a lot of problems, a lot of challenges. And if you think about it, the academic community spent about 10 years trying to understand two-level systems, understanding how to optimize the highest quality of qubits. And do you know what they came up with? Two-level systems. Where's that come from? Dielectrics. It comes from dielectric loss often. It comes from any different type of layer, any of these interfacial layers. All of these things create additional loss mechanisms and are performance limiting. But for some reason, we seem to sacrifice that for the fact that we have this scalability in terms of a solution. Now, we can still show that we can get pretty good performance from this. Google again. So this is the sycamore chip, and you'll see this one is a flip chip. It's incredibly state of the art, but you can still even see that it's got all of that wiring fanning to the edge. Okay, so a ton of clever engineering, ton of stuff is happening. This really is where OQC and our academic founder, Peter Leak, took that step back and said, how can I approach this in a really different way? What would I do if I was redesigning a qubit from scratch for commercial purposes with that scale, quality, and functionality in mind? And this is where he came up with OQC's unique IP, which is the coaxmon. Now, what we've done, we said 1D, okay, not good enough, 2D is not good enough. We are going 3D and we are liberating ourselves from 2D constraints. We are taking our qubits out of plane. So what we can see on the left here, and you can check out papers for more scientific details that are referenced at the bottom there, is a diagram of the coaxmon.
Ilana, we just time. Yeah, so if we can just another minute or two, because
yeah,
we.
No worries.
Thank
I'll
you.
show you the interesting stuff. Thank you. So what we have here is the coaxmon, and it's a silicon or sapphire substrate. On one side, we have our qubit, which is a transmon. It's got an inner and outer and a Joseph junction in between. On the other side, we've got our LC resonator, which has got our spiral. These are mode matched really neatly to our control and our readout ports that come down either side and are never galvanically connected at all. I will skip through, I promise, very quickly, but I just want to get to the results if that's all right. Then here we go. That's just qubit measurement stuff. Look it up in the paper. Vertical wiring, really cool. Really low crosstalk is what's really, really important in this, because you've got that really low mode matching. And here we go. So this is some of the results. You can see Peter Spring's talk from APS. This is out from the University of Oxford. Here you've got our T1 times, our T2 times, also demonstrating that there is incredibly low crosstalk, primarily because you've this incredible mode matching. And this is an example of one of the devices here as well. Sorry, so giving you a history of superconducting qubits, not talking about our own. Just to highlight, of course, that a qubit is part of a process of an entire computer. None of this will be possible for the community as a whole without partnerships and without making sure that we collaborate. So that's part of our strategy. We have the UK's most advanced and only available quantum computer in the country. Here's a pretty picture of it. We're building a world-class company as well as world-class technology. We are hiring. Please join our team. It's an incredible place to work and lots to think about. And that is it from me. Thank you so much.